Okay, so welcome everybody. Hope you've all had a good week. I started the recording now, so if you want to type your name into the chat so we have the record for your attendance, now is a good time to do it. If you typed your name in before we started the recording, then you won't have a record, so please do it again. All right, so I hope everybody is doing well. Excited to be back in a regular swing of things so that we'll be meeting every week in October. Let me move over here. Okay. Um, so I guess we don't have Deborah in class yet, so I still am waiting for her to tell us what's happening with the certification. I wanted to let everybody know, everybody who had name mistakes on their old certificates, I've printed out the new certificates. I have them, and I have to find out when to give them to Mr. Randolph, but then somebody will carry the corrected certificates to Liberia, hopefully pretty soon. Um, I have to ask Mr. Randolph exactly when that will happen, and then hopefully everybody can get this year. I can find it difficult to share knowledge. Somebody please help. I don't understand what that comment means. Um, but okay. Yes, James, we're gonna go to the homework problems at some point soon. Okay, so I just want to give a little review for today. So we're gonna finish see if anybody has a problem from the previous week about the applications of logarithms. If we have something, yeah, she's in the States, but she's not close to me. I'm not. She's not going to be in my city, and I'm not going to be in her city. So I don't think I'm going to be able to get it to her this week because she's going back to Liberia on Monday, if I believe correctly. So I can talk to Mr. Randolph, but I don't think he's going to be able to get it to her because she's in Washington, D.C. She's 200 miles away. I don't think I'm going to be able to get the new ones to her this week. Um, I spoke to her. She's not coming up to New York and she's not coming up to Philadelphia, which are the places where it's reasonable for me to get this week. So I'm not going to be able to reach her in Maryland. Um, okay. So so let me first just say I want to go back to the previous week because nobody came up with a problem then. Does anybody? Oh, this is good because Linford has just entered the room and he had a problem that he wanted to share, a problem involving applications of logarithms or exponentials. I would say preferably logarithms because that's what we talked about in this year's program. But if we want to do one with exponentials, that will work as well. So, Linford, I don't know if you have access yet, but do you want to give us your problem from last week about exponentials? If you want to either share it in the group or write it down, and I can transcribe it for you. Or does anybody else have a word problem involving applications of logarithms or exponentials that they want to share for this week before we move on to mensuration to our topics today? Okay. So if nobody has a problem we want to do right now, we can. Oh, okay, I see. All right, so this time is not so good. All right, we'll do our best, Prince. And for next semester, the time, by the way, we're going to keep this time for this semester, for until December. But for the spring, if we want to change the time that class meets, I can send out a survey, and if there's a time that works better for people in the spring, we can do that time instead. Okay, my schedule for the spring is pretty flexible. For the fall, we'll keep it the way it is now, but for the spring, if people want a time change, I can try to ask when a good time is for everybody. Okay, so through December, we'll keep this class, but then in the spring semester, we can maybe change things. Okay. All right, well, let's skip this. We can come back to this now if we want later. Okay, so I want to just recall what we talked about last week with mensuration. Right. So mensuration is the act of using geometry to compute lengths and areas and volumes of shapes. And we talked about a lot of different formulas last week. So we had one-dimensional formulas, length, perimeter, circumference, two-dimensional formulas measuring areas and surface areas, and then we had three-dimensional formulas which were measuring volume. And if we have a d-dimensional formula, I'm just using a letter D to stand in for either 1, 2, or 3. We saw last week that if you multiply all of the length inputs to the formula, that shouldn't say D, sorry, that should say C. If you multiply all the length inputs to the formula by C, then the resulting output measurement gets multiplied by C to the D. So for instance, this is a lot of letters, but if you calculate a surface area, if you calculate a surface area and then you multiply all of the length inputs by C, then the surface area gets multiplied by C squared. That's because in this case, it's a surface area, so D equals 2. That's a two-dimensional thing, right? Even if your shape that has the surface area is three-dimensional, the actual thing that you're computing is a surface area. That's a two-dimensional measurement. It's not a volume, which would be a three-dimensional measurement. So when you have a surface area and you multiply all of your length inputs by C, that means that the surface area is going to get multiplied by C squared. And the nice thing about this is that it works no matter what the shape is. Okay, it doesn't matter whether it's a sphere or a pyramid or a box. As long as you're making a two-dimensional measurement, then anytime you multiply all the length inputs by some constant c, then the surface area is getting multiplied by c squared, no matter what. Okay? So, as an example, we have this first homework exercise, which I think several people have given the answer. So I drew this cloud. It doesn't really matter what the shape is, but I drew this cloud. And so if I say that the area of this is 200 square units, then now if I draw the same cloud 5 times as big, I mean, this isn't really going to be 5 times as big, but if I do this, if this is 5 times as big, okay, then what is the area of this figure when I draw it 5 times as big? So I saw several people answered it. It's a pretty quick question. Does somebody want to just give the solution now? All right, so I saw several people wrote the answer. Okay, so I see 1,000, I saw 5,000, I saw 500. Um, does anybody want to give their work, their justification for their answer? And remember, we're stretching by a factor of 5 in all directions. So the length is stretched by 5 out this way, and then the height is also being stretched by 5. We're stretching it by a factor of 5 in every direction. Well, what kind of measurement are we making? We're making a measurement of area. So how many dimensions is that? Two dimensions, right, exactly. So if it's two dimensions, What do we have to do? We have to take our original area and now we're multiplying it by 5. We're stretching all the linear inputs, all the length inputs by a factor of 5. But since it's 2 dimensions, what do we actually have to multiply by? So what does this 200 need to be multiplied by to get the area of the new figure?
We multiply by 25.
Right, exactly. Right, by 25. So we have to do 200 and we have to multiply it not just by 5, but we have to multiply it by 5 squared. And that's because area is a 2 dimensional measurement. Okay, so area is 2 dimensional. So we have to multiply it by 5 squared. And so what that means, so this becomes 200 times 25, and this comes out to be 5,000. Okay, exactly. So Benbia Linford is correct. Exactly. So we have 5,000. So when you stretch this cloud by a factor of 5 in every dimension, then the new area is 5,000, not 1,000, because you need to multiply not by 5, but by 5 squared, because we're doing a 2 dimensional area. And you can answer this even without knowing the formula for the area of a cloud, right? I mean, I just drew some shape that you don't know the formula for the area, but you can still figure out what happens to area when you make this kind of stretching. Okay, so the area is proportional to the square of the length inputs. Okay, any questions? What if it's not in 2 dimensions? Well, then it's a different thing. So if I asked what happens to the perimeter, for instance, so the perimeter of this is a 1 dimensional thing. So I mean, I didn't tell you what the perimeter is, but let's say the perimeter of this was, I don't know, let's say the perimeter of this was 80 square units. Oh, sorry, was 80 units. Then if I stretch it by a factor of 5 in every direction, then the perimeter just gets multiplied by 5 because perimeter is a 1 dimensional quantity. So if I stretch it by a factor of 5, then the perimeter doesn't get multiplied by 5 squared. It only gets multiplied by 5. So you have, instead of 80 times 5 squared, you would just have 80 times 5. So the new perimeter would be 400 in that case. Well, what if you were asked in 3 dimensions? So the way I drew this can't be 3 dimensions because it's a 2 dimensional cloud. But if I drew you some 3 dimensional cloud, which I can't draw right now, and then I asked what happens to the volume when you stretch it in every direction by a factor of 5, then the volume would have to get multiplied by 5 cubed, 5 to the 3. So you would actually multiply the volume by 125 instead of just by 25. So, right, it's exactly the idea. If it's a 1 dimensional thing, perimeter, then it gets multiplied by 5. If it's an area, like in this question, it gets multiplied by 5 squared, which is 25. And if it's a volume, it gets multiplied by 5 cubed, which is 125. Okay. Is that clear? Mhm. Okay. Good. Okay, so let's go on to the next problem. So, homework exercise number 2, this is a little more challenging. So, can we derive the surface area for the formula for a square pyramid? I'm going to draw it like this. A square pyramid with with side length s, with height h, and side length s. Okay, so maybe let me write this h over here. Okay, so the base side length is S and the height is going to be H. And then, oh, no. What did I do here? Okay. and the side length is h. And so we want to calculate the surface area, right? No, what am I doing here? We want to calculate the surface area. Okay. And so in order to, so for the first thing is to just derive this surface area formula. And then the second thing is we should be able to verify that if you multiply all of the inputs by c, then the surface area will get multiplied by c squared, right? This is what we've said happens. If you have a surface area formula, if the inputs, meaning the side length and the h, are multiplied by c, then the entire surface area should get multiplied by c squared. So for a check that we actually have our surface area correct, we need to check to see if we multiply everything by c, does the surface area get multiplied by c squared? So I'll take some input, but let me just start with this set up. So what's the surface area? Well, this is a square pyramid. So the surface area is going to be the area of the square, right? There's a square on the bottom here. That's what a square pyramid is. And then plus, well, the pyramid has four triangular faces, right? One for each side of the square. So it's going to be 4 times the area of the triangle, right? So the square is pretty easy. What's the area of this square? What's our formula for the area of the square on the bottom? S squared, right? It's just a square. The side length is s, right? So the area on the bottom here is s squared. Okay. So that's s squared. That's not a problem. And now we need to figure out the area of the triangle. And now we have this. Oh, I see somebody has posted a message here. Okay, so there's Linford Benby. Okay, first answer is correct. Right. Okay, exactly. So, okay, so the point is what we need to do, I'll draw this in purple. What we need to figure out is the height of one of these triangles. So I'm going to draw this in purple over here, and I'm going to call it script L. Right, so this is exactly, okay, so Linford has done a great solution, so everybody can read it if you want to see it on the site, but on the chat, but this is exactly right. So we need to know what this L is, because if we have this triangle, we can see that if we write this triangle flat, the triangle looks like this. It has side length S, or base length S, and then the height of the triangle is L over here, right? Because I'm drawing this L, which is really the height of the triangle. H is the height of the pyramid, but it's not the height of the triangle. The height of the triangle is actually this length L. And so we know that this area of the triangle here, this is going to be 4 times 1/2 base, which is S, and L, which is the height, or this simplifies to 2SL. Okay, so the question is, what is L? Right, we got to figure out what this slant height is. This L over here is this L we could call the L is the slant height. What do I do here? So L here is going to be the slant height. Okay, so how do we figure out L? Let's see how well it's explained. Okay, right. So Linford writes the answer here. Everybody can read it in their chat. But the idea is, how do we figure out L? Well, look what we have here. We have a right triangle here. H goes to the center of the square. L here is the hypotenuse, and I can use a new color. Maybe I'll use green here. Let me just write this triangle over here, right? This is a right triangle that I can draw inside the pyramid, right? Well, we have a right triangle where I'll draw it using the same colors. So I have a red height and then a green base and a purple hypotenuse, right? And this is L. This height here is H. And then we need to know what is the base. Right, so what's the base here? Well, we know that this height goes to the middle of the square, and the side length of the square is s. Yeah, William? So the length of the distance from the center of the square over to the side of the square is what? That is s over 2, right? Right, so sorry, somebody what's going on with that? Sorry, I'm trying to mute everybody. Okay. Okay. Okay, so what do we have over here? This base over here, let me write it in green, is s over 2. Okay, good. Victor, so do you want to give so what's the formula for L since we have this right triangle over here? Oh, not s squared, sorry. S divided by 2. S divided by 2. Mhm. So we know that by the Pythagorean theorem, okay, again, please only turn on your mic if you're making a comment. Otherwise, please keep your microphone off. Okay, again. Why is this not muting? Okay, so sorry. Again, please keep your mic off unless you're answering or asking a question. Okay. Um, all right. So this is the right triangle. It looks like this. So by the Pythagorean theorem, we get that L squared is equal to h squared plus s over 2 squared. Or L is equal to the square root of h squared plus s over 2 squared. Right? This is exactly what we see over here in Linford's answer, right? So what this tells us, once we've calculated L, we have 2SL, and that's the same thing as 2S times square root of h squared plus s over 2 squared. Okay, so we have this somewhat difficult formula, right? We have an s squared, and we have a 2s times square root of h squared plus s over 2 squared, right? So I'm just going to write that whole thing here. So what we end up getting is s squared plus 2s square root h squared plus s over 2 squared, right? Okay, so probably not a formula that you want to memorize, right? The formula that's going to be a little bit hard to memorize, but we can derive it using standard results of geometry, right? The square part is easy. The triangle part you need to write, it's going to have a base and a height. But even that height, you need to figure out what that L is in order to get a formula that involves only S and H. So in the end, this is your formula for the surface area of the pyramid, and it involves only an S and an H. So this gives us the first part of the problem. Okay, so it's 2SL, but that L you express in terms of S and H, and we get S squared plus 2S times square root of H squared plus S over 2 squared. So we'll do the second part of the problem, but before we do that, are there any questions on the first part here? Yes, sir. Why S over 2? Okay. So the question why S over 2, so I've tried to label it with the colors. So S over 2 is the green side here, right? Because this side, this triangle is red, green, purple. And so I drew it here red, green, purple. So S over 2 is the distance from the center of the square to one of the sides, right? Because this pyramid comes down in the center of the square. So if the entire side length of the square is S, when we're just going from the center out to the side, that's going to be half the side length of the square, right? Because if we went all the way across, that would be S. So instead of we're only going from the center to the side, that's going to be S over 2, right? So it's not going to be S over 4 because we're not looking at area. We're just looking from the center of the square out to the side. So that's going half the length of the side of the square. Because if you did that and you did it again, you would get the same length as the side of the square, right? Because this is a parallel line on a square. So a line across the middle of the square has the same length as the side. So if we go the line on the square just from the center to the side, that's going to have half the length of the side. Okay? Okay, you're welcome. Is that okay? Okay, yeah, S over 4 doesn't quite work. Maybe let me show you just in another diagram. What happens here? If I just draw a square with side S, 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 and now I draw a line from the center of the square to the edge of the square, and I draw another line from the center of the square to the other edge of the square, the whole green line is S, and the two parts definitely have to just be 1/2 each because it goes from the center, S over 2 and S over 2. Right? S over 4 wouldn't work because then the entire length would just be S over 2. And the whole length of this green line is certainly equal to the length of the blue line, right? So they both have to be S over 2 to get it to work. Is that okay? Okay, so going back to the final formula. Okay, so this is what we get. S squared plus 2s square root of h squared plus s over 2 squared. Okay, so I'm going to copy that here. So I'm just going to copy that. So let me see. So surface area is equal to, we saw s squared plus s square root of h squared plus s over 2 squared. Okay, this is our surface area. So now what happens? Now let's replace s with cs and h with ch, right? This is what we're doing. We're scaling our inputs by c. So what do we get? We get cs squared plus cs square root of ch squared plus cs over 2 squared. Simplifying this, this becomes c squared s squared plus cs square root of, well, in the middle, I get c squared h squared. That's ch squared. And then plus c squared s squared, or maybe I'll write this, yeah, c squared s squared over 4. And now remember how this works. I'm going to write this as c squared s squared. Remember, if I have a c squared underneath the square root. So plus cs, I can write this as c squared and then h squared plus, and I'll actually rewrite this as s over 2 squared. And now remember what happens with square roots. If I have a c squared under the square root, that corresponds to square root of c squared. So when I pull that out, it just becomes a c. So this is c squared s squared plus cs and then another c times square root of h squared plus s over 2 squared. Let me put it up here just so that you can see it. The print gets a little bit bigger, right? And now here's a c squared and here's a c squared, right? I have CSC. It's the same as c squared. So this now becomes, I can factor out a c squared. That's c squared plus times s squared plus s square root Oh, sorry. This should be, did I miss a two somewhere? There should be a, sorry, there should be a two everywhere here. Two, 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 two. There's just twos everywhere here. Plus 2s square root of h squared plus s over 2 squared. Okay. And what do we have here? This was our original surface area, and our new surface area is the same thing, but multiplied by c squared. So we do verify. So we verify is that, or maybe I won't say verified, I'll say verified. We have verified that surface area gets multiplied by c squared, which is exactly what we wanted to do, right? We want to show that even with a complicated formula like this, it still has the correct transformation property. If you multiply all of the inputs by c, then the output gets multiplied by c squared. That has to be true because this is an area formula. It's a surface area, but it's still an area. Okay. I'm sorry the network is so bad, Linford. I'm glad you were able to share your answer, though. That came through clearly, and that was very helpful. So if anybody wants to see this derivation again, they can look at what Linford sent in the chat, or you can read it over here. But the point here is that, yes, so the surface area gets multiplied by c squared. Let me do that. Gets multiplied by c squared over here. Okay. Yes, okay. I'm sorry the internet is giving so much trouble. Okay. All right. Any questions on this anymore? Okay. All right. No more questions. Let's move on. Okay, so what's today's topic? We're going to stay on geometry. We're going to move a little away from mensuration. So today's topic is the centrality of triangles to plane geometry. So when you do a geometry curriculum, you're teaching geometry almost everywhere. I assume it's the same. You spend lots and lots and lots of time on triangles. Now, the question is, why do you spend so much time on triangles? Well, and let alone trigonometry, even without trigonometry, you usually spend more time on triangles in geometry than on any other shape, right? So why do you spend so much time on triangles? Well, one reason is that if you understand triangles, that's basically enough to understand all polygons, all kinds of any kind of straight plane shape, right? If I draw some strange polygon, right? I mean, this is some strange decagon or something. I can always draw lines. This can be broken up into triangles, right? I can triangulate it if I want to, right? I can always, if I draw enough lines, I can break it up so that this thing becomes just a bunch of triangles together. So just like in number theory, if you have a composite number, you can break it up into a product of prime numbers. Somehow the prime numbers are the building blocks of arithmetic, of numbers. In geometry, the triangles are the building blocks of geometry. Okay, at least of plane geometry and of plane geometry involving straight lines, right? So maybe plane geometry involving circles is a little bit different. But for plane geometry involving straight lines, everything comes from triangles. And in general, It's very difficult to memorize a lot of formulas for quadrilaterals and pentagons and hexagons and everything. So you don't want to memorize formulas for higher dimensional polygons because they're just very hard. But triangles, it's more reasonable to memorize all the formulas that you need for triangles. And then anytime you have some kind of geometry problem that involves bigger polygons, usually you can solve it by breaking it up into triangles in a good way. Okay? So this is going to be kind of the topic today is how do you reduce everything to triangles? We're only going to give a very quick review of triangles. We're not going to go and prove everything about triangles. If people later want to go over proofs, we can do that, but not today. But today we're going to take triangles for granted and we're going to show how you can get lots of other things from geometry without knowing anything except how to do triangles. Okay? So this is the idea that it's hard to memorize formulas involving many-sided polygons. I don't know the formula for the area of a pentagon, and I don't know the formula for the area of an octagon or anything like that, right? But if you're given something where you have to deal with a bigger polygon, then you can do this by breaking them up into triangles and just using what you know about triangles. Okay? So let me give so this is over here is what I call the triangulation. Okay, it's a triangulation of this little fish-looking polygon. Okay, okay, good. All right, okay. 1 second. Okay, so what do we know about triangles? Basic facts. There's a lot more facts than we know about triangles, but these are the ones we're going to use today. So we know that the angles in a triangle add up to 180 degrees. Is something we should be able to prove, but we're not going to prove it today. We know that the area of a triangle is 1/2 the base times the height, or B is the base and H here is the height. We know that every triangle, this is a little bit harder to prove, but every triangle has a unique circle that's tangent to each side. This is called the incircle. So I can draw a circle, let's say here and here and here. I can draw a circle that's tangent to each side of the triangle. I'm not going to do the drawing so well, but okay, here we are. This is a circle that's tangent to each side of the circle. This is sometimes called the inscribed circle or the incircle. I'll label this here. This is the incircle. And then at the same time, you have every triangle, there's a circle that passes through all three of the corners. That's called the circumscribed circle, the circumcircle. Okay, so this would be called the circumcircle. Okay, and this is a fact that you can prove, although I'm not going to prove it today, that every triangle, there's a unique incircle and there's a unique circumcircle. Okay, and this is the incircle is that it's tangent to all three sides of the triangle, and the circumcircle is that it passes through all three corners of the triangle. And if you want to review triangles for your geometry, an excellent reference that has all of the basic facts about triangles is Chapter 11 of The Art of Problem Solving, Volume 1. So I sent this to you in soft copy on the chat at the beginning of the fall. Let me just show it to you for now. Let me show you my screen. Where are we? Here we are. So this book that I sent in soft copy earlier, and I can send it again into the chat room at the end of the class. If we look at chapter 11, it's a 20-page paper, a 20-page chapter about triangles, and kind of has everything that you need to know about triangles in one very quick chapter, okay? So they say, and they even say it here, nearly all of geometry comes down to the simple three-sided figure, the triangle. So the triangle is going to help you do all sorts of geometry questions And you see this starts from the very beginning. What is a triangle? Acute, right, obtuse, scalene, isosceles, equilateral, all the different kinds of triangles. And then it goes on, talks about the parts of a triangle, the triangle inequality, Pythagorean theorem, congruent triangles, congruency theorems, um, similar triangles. What else? A little bit of an introduction to trigonometry and little introduction to trigonometry, formulas for the area of a triangle, and and then some helpful hints, and then lots of problems afterwards. So lots of problems to solve about triangles. So I'm not going to go through this carefully, but if you want to review your triangles, you can look at chapter 11 in this book that I sent you, and it's about 20 pages long, and it gives a good summary of kind of everything that you need to know about triangles. Okay, so let me stop the share. Let me share here again. Where am I? Share. No, sorry. Okay. So, but for today, we only need a few simple facts about triangles. So we need this statement about the angles, this statement about the area of a triangle, and that each triangle has a unique circle that's tangent to each side, and also a unique circle that passes through all three corners, and that's called the incircle, and this is called the circumcircle. Okay. Any questions? Okay. Let's move on. Okay. So let's one case of doing geometry by reducing to triangles. So we got angle sums. So what is the sum of the angles in an n-sided polygon? And what's the measure of each? Oh, so uh, I should say here, if the polygon is regular, then what is the measure of each angle? So let's imagine I have, a seven-sided, let me just draw some polygon. Oh, hold on. Okay. So I'm drawing this polygon right here. It has seven sides. It's not a regular polygon. I want to know what is the sum of the angles. Well, in general, I don't know quite how to do that, but the theme of today is when you're trying to do geometry, divide everything into triangles. So let me divide it all into triangles like this. I'm just going to pick a corner. It doesn't matter which corner I pick. And I'm going to draw the line from that corner to each of the other corners. Okay, draw the line to each other corner. And what do we have? It looks like here we have five triangles. 1, 2, 3, 4, 5. And what we see is that sum of the angles in the heptagon, it's called a heptagon, that's a seven-sided polygon, equals the sum of the angles in all five triangles. Right, because I look at this angle, part of it is in each of the angles, each of the polygons, and every angle in the heptagon comes from one of these angles in one of the triangles, right? But we know, so James is correct. So heptagon is 1260 degrees, and no, not quite 1260 degrees. Okay, so we have the sum of the angles in all five triangles. We know that a triangle is 180 degrees, so total sum has to be 5 times 180 degrees, right? Because this 180 degrees, this is a triangle. And we divided the heptagon into five triangles. So the total sum here ends up being 900 degrees. right? Exactly. And so I can say in general, this method divides an n-sided polygon into n minus 2 triangles, right? Because how many triangles do I get here? Well, how many lines do I draw from this point? Well, I, you know, I have I have basically n minus one other points to draw to. And so the number of triangles that I get is this first side doesn't give me a new triangle. And then each side after that gives me a new triangle. So I draw this, I get a new triangle. Here I get a new triangle. Here I get a new triangle. Here I get a new triangle. And then here I get a new triangle. So not counting these 2 points, you get a new triangle for each of the lines that you draw here. So what that means is if since there's n vertices, n corners, you're going to end up with n minus 2 triangles. Okay, so you get an n-sided polygon becomes n minus 2 triangles. So that means that the total angle measure is equal to n minus 2 times 180 degrees. Okay, so the total angle measure for an n-sided polygon is going to be n minus 2 times 180 degrees. So for the heptagon, this has 7 sides. The total angle measure is going to be 7 minus 2, which is 5 times 180 degrees. That's 900 degrees. And you solve this by just dividing it all into triangles. Okay. Okay. And so if the polygon is regular, remember that just means that all the sides and all the angles are the same. Then each angle is going to be n minus 2 times 180 degrees divided by n, right? Because it's going to be the total angle measure divided by the number of angles, the number of vertices. So for a heptagon, it's going to be 900 divided by 7. That's actually not an integer. So it's about 128 degrees per angle, but it's not an exact integer number of degrees, right? So I'll write that on another slide. But before I go to that other slide, I just want to ask, are there any questions about this procedure for getting the total angle measure of a polygon by dividing it into triangles? Okay, 128.6. Yeah, that sounds right. Okay, good. So let me just add another page just to finish the problem for a regular n-gon, meaning an n-sided polygon. Each angle has measure, well, we have n minus 2 times 180 degrees divided by n. Okay? Yeah, exactly. No questions, the same as n minus 2 times 180. Exactly, right? So each angle has measure n minus 2 times 180 degrees divided by n. Okay, good. Okay. Okay, so what's another formula for the area of a triangle? So let's say that I have a triangle and I'm going to let R be the radius of a circle that's inscribed in it. So I'm going to draw this triangle large. Okay, so let me draw this big triangle. Okay, and I'm going to draw the circle that's inscribed in this triangle. So it's probably just going to pass through here, probably roughly straight up through here. And then, what do I want to say? That's probably going to go up to here. So let me just try to draw a circle, try to draw the in circle. It's always a little tricky to draw. I didn't do such a good job with that. I didn't do such a good job drawing that circle, but let's allow it for now. Okay, so let's imagine this is our circle that's drawn inside. And I'm going to let R be the radius of the circle inscribed in it. Okay. What do I want to see? Okay, I'm going to let R be the radius of the circle inscribed in it. So let me just call this ABC, label the sides of the triangle, and I'm going to label the sides of the triangle here as A, C, and B. Okay. All right. So what's the formula for the area in terms of R? So this is going to be, what I'm going to do is I'm going to be dividing this triangle. Let me draw the center of this circle. Okay, so one thing we know, and maybe I think it's actually a little bit lower. I'm going to draw the center of this circle over here. And so what I'm going to do is I'm going to draw some lines. I'm going to write this triangle as a union of a bunch of other triangles. So I'm going to draw the following lines. I'm going to draw 3 radii of this circle. I'm going to draw these lines where the triangle, I draw it from the center to the places where the circle is tangent to the triangle, right? So all of these are radii. So all of these have length r. And now I'm also just going to draw the lines from the center of the circle to all of the corners of the triangle. Let me make this a straight line. Okay. So I'm going to draw all of these lines. And let me call this, a lot of times you call the center of a circle, you call it O. I'm going to call that point O in the middle. Okay. So what do I know? So I know that the area of triangle ABC, I'm dividing it into these 3 triangles that all come from the middle. So this area of this triangle is equal to the area of triangle BOC plus the area of triangle AOC plus the area of triangle AOB. Right? BOC is this triangle here. AOC is this triangle here. And AOB is this triangle here. So I've divided the big triangle into a bunch of little triangles. Okay? All right. So now I need to use one other fact about a circle, which is that if you draw the line from the center of a circle to a tangent line to the circle, it always forms a right angle. So all of these angles are right angles. Everywhere here is a right angle, and everywhere over here is a right angle. All of these places where they hit the edge is always a right angle. This is a fact. So let's look. What is the area of triangle AOC, for instance? Well, this is a triangle. It has height r because this makes a right angle. So this is the height. And it has, the base is b. So the area of this triangle is 1/2 BR. Okay, so let me draw this in purple. So the area of this triangle over here is 1/2 BR. That's the area of triangle AOC. Similarly, what's the area of triangle AOB? Well, you have to kind of turn it on its side in your mind, but you can think of C as being the base and R as being the height. So the area of this triangle is going to be 1/2 CR. And lastly, what's BOC? You again have to turn this on its side in your mind, but If you can think of it that way, you can think of it as having A as the base. Let me rewrite A a little bit closer to the triangle. A is going to be, oh, sorry, let me put it in blue. Uh, okay, so here A is the base and R is the height. So we get for this area right here is 1/2 AR. So when we add this together, what do we get? We get 1/2 AR plus 1/2 BR plus 1/2 CR, or in other words, R times 1/2 A plus B plus C, right? And A plus B plus C, this is the perimeter, right? A plus B plus C over here, this is the perimeter. I'm just going to abbreviate it as per. So this is for perimeter. So we see that the area of the triangle is R times 1/2 of the perimeter. This 1/2 of the perimeter is sometimes called the semi-perimeter. So we can write this as RS as a formula for the area of the triangle, whereas I just say S here is equal to what's called the semi-perimeter, which is equal to 1/2 times the perimeter. Oh, no, no, stop. 1/2 time. No, what am I doing here? 1/2 times the, no, no. Okay. So semi-perimeter, which is equal to 1/2 times the perimeter. So it turns out that the formula for the area of this triangle is just RS. It's a very nice formula. Okay, if you know what the radius of the incircle is, then the area of the triangle is just that radius times the semi-perimeter. And the way that you do that is by dividing the triangle up into 3 little triangles and calculating the areas of each one. The area of this one is 1/2 RC, this is 1/2 RA, and this is 1/2 RB. Okay, so this is another formula for the area of a triangle, and it's one that's relatively easy to derive. You do need to know this fact that the radius is perpendicular to a tangent line. And so what I want to show on the next slide, I'll take questions here first, but what I want to show on the next slide is that you can use this not just for triangles, but for basically any polygon that has an inscribed circle. So before I move on to that, are there any questions about this example? How do we end up with RS? Right. Well, so the formula here is 1/2 AR. Oh, sorry. Right, the formula here is 1/2 AR plus 1/2 BR plus 1/2 CR. And I factor out the R, so that's R times 1/2 times A plus B plus C. And 1/2 A plus B plus C is S, right? Because A plus B plus C is just the perimeter. And so 1/2 of that is the semi-perimeter. This is the definition of the semi-perimeter. It just means 1/2 of the perimeter. So we end up with R times 1/2 of the perimeter, and that's going to be RS over here. Does that answer the question? Okay, great. Other questions? Okay, so now let's apply this. So what happens now? Let's say we have an n-sided polygon and assume that there is an inscribed circle. And I want to be aware that when you have a polygon with more than 3 sides, there might not always be an inscribed circle. Okay, so for triangles, there's always an inscribed circle, but for other polygons, there might not be. But let's say that you do have an inscribed circle. So I'm going to draw a pentagon here. So let me draw an example. Here's a pentagon. I'll draw it as just a regular pentagon. No, no. Okay, so I'm going to draw a regular pentagon. And let's just imagine that we have an inscribed circle that I'm going to draw like this. So this is a pentagon. And I have some center here. So, and let's say that again, we have inscribed circle has radius r. And I'm going to label the sides of this pentagon. Let me just label them A, B, C, D, E. Okay, I don't even need to label the corners. I'm just going to label the sides. So let me draw the same diagram here I did with the triangle, right? So in red, I'm going to draw all the lines from the center to the tangency points. And in green, I'm going to draw all the lines from the center to the corners. Okay, so let me draw in red. That's going to be just this line here, all these lines from the center to the tangency points. Okay, and now in green, I'm going to draw all the lines from the center to one of the corners. Okay. Okay. All right, so the diagram looks a little bit complicated, but what I want you to to focus on is that the area of the pentagon is divided into these 5 triangles that are formed from the green lines together with a side. So you have this triangle here on the top, then you have this green triangle, then this green triangle here, this green triangle here, and this green triangle here. So the area is the sum of the areas of 5 triangles, each with the green sides and base A, B, C, D, or E. That's what makes these 5 different triangles, right? And we know that all of these red lines have length r, right? Because they're all just the radius of a circle. They're all r. And again, we know, like before, every time the radius hits one of the sides of the pentagon, it's always making a right angle because it's tangent. So all of these are right angles. Right, and so there we are. So James is going to get the same answer, right? So what is the area? As James writes, well, let me look at this triangle. This is a triangle. The height is r and the base is a. So it has area 1/2 r times a. Look at this triangle. The height is r, the base is, well, I'll go over here. The height is r and the base is b. So this triangle has area 1/2 r times b. And then the pattern continues. So we get 1/2 r times c plus 1/2 r times d plus 1/2 r times e. Or I can take this as being r times 1/2 times, and then I'll write a plus c plus d, a plus b plus c plus d plus e. And this whole thing here is the perimeter. And so what you end up is getting exactly the same formula, r times 1/2 times the perimeter, or in other words, you get that this is exactly r times the semi-perimeter, right? Where here s is equal to 1/2 times the perimeter. Okay. Okay, so what this shows is that if you have any polygon with an inscribed circle, this exact same formula works for the area of that polygon. You can always get that the area is just RS. And it works by taking a polygon that can have as many sides as you want and instead just dividing it into triangles. Okay? So the area of a polygon with an inscribed circle can always be given by the formula RS, and it doesn't matter how many sides the polygon has. And the way we show this is by dividing it into triangles. So you can always use RS as the area of a polygon. Okay. Any questions? Can we derive another formula considering circumscribed after this example? Yes, but not today. We won't have time to do that. I want to do this. So there is a formula. It's ABC over 4 times the radius of the circumscribed circle, but that I don't want to. We can derive that, but I don't have time. I didn't prepare it for today, so I don't want to do it spontaneously. Maybe we can do it next time. All right. Other questions? This one generalizes to general polygons very easily. So that's why I wanted to do it, because it illustrates how by dividing something into triangles, you can make it work. Okay. What happens here when we have a regular polygon? So let's assume that we have a regular n-sided polygon. That just means that all the sides are the same and all the angles are the same. So when you have that, you definitely have an inscribed circle. So what does our area formula yield? Right? So maybe I'll draw this same picture. Actually, I want to see if I can copy paste the same picture. So if I do this, can I copy? Got it. How do I copy this here? Copy. Okay, let's try this. Oh, there we are. Okay, good. I can paste this. Okay, good. All right, I learned how to copy paste. So let's imagine. So imagine that A equals B equals C equals D equals E, and all angles are equal also. Okay, and what I'm gonna do is I'm gonna erase everything on the inside. I'm just gonna leave. Actually, wait, hold on. I'm just gonna erase these lines. I want to leave the circle itself. Oh, let me just draw this circle. Okay. So I have my center, and I know that I'm just going to look at one of these triangles, right? So we know, what do we know? We know that the area is equal to RS. So the question is, can we get a formula for the area just in terms of S? Can we get a formula for the area in terms of S and just N, which is equal to the number of sides? Yes, we get a formula in terms of S and the number of sides, S and N. And well, the question is, well, we have this R over here. Let me draw it in a different color. So we have R. This is R. And we know this over here, this R divides the side in half because it's a regular polygon. So this over here is S over 2, right? And this is a right angle. Okay. So now what do we know about angles? Well, we know, sorry, we know that each angle has measure, we calculated this before. Each angle has measure n minus 2 times 180 degrees divided by n. Right? We showed this a few slides ago. Measure of each angle is the total angle measure, which is n minus 2 times 180 degrees, and then you divide by n. So if we look at this triangle, if I want to look at this triangle over here, what do I have? I have a triangle where this side is r, this side over here is s over 2, and then I have an angle. What's the angle over here? Well, the angle here, this bisects the angle. So this angle here is 1/2 the measure of each angle. So if it's a pentagon where each angle is 108 degrees, that's 3 times 180 divided by 5. Where each angle is 108 degrees, that means this one will be 54. But in general, this angle is just going to be n minus 2 times 180 degrees divided by 2n, right? Because it's going to be half the measure of the general angle. Okay, if you have a question, you can type it into the chat or later on, and I can answer it. Okay, so that's going to be this. And so what we want to know is, can we figure out what this R is in terms of just n and s? And the answer is we can with a little trigonometry. So what we have is that the tangent of, or maybe actually this is, never mind. Forget it. This is more complicated than we need. Let me do it more easily. Maybe what I should do is instead this angle over here. Look at this angle over here. So this angle over here is we're dividing the polygon into n triangles, and this angle is half of the central angle in the triangle. So what we actually get here is we have this right triangle. This is r, this is s over 2, and this angle over here is a full circle, 360 degrees, divided by 2n, right? Because you have n triangles, and this angle is half the measure of the angle in the triangle. Remember, if we did this as a full circle, we would have 360 degrees, right? And so the part that we get over here, this is 1/n of 360 degrees, and then this is half of that. So in fact, we divide by 2n instead of by n. And so using a little bit of trigonometry, what we get is that tangent of 360 degrees over 2n is equal to the opposite over the adjacent side. That's the tangent. And that's equal to s over 2 over r. And what this solves for is this tells us that r is equal to s over 2 divided by the tangent of, sorry, semi-perimeter is, sorry, I'm using this area S for n. Sorry, I made a mistake here. I apologize for this. This area is actually, I was using S for a side and S for semi-perimeter. That's why I got confused. If S is the semi-perimeter, I apologize for having to back up to this. So if S is the semi-perimeter, right, S is 1/2 the entire perimeter. So if I look at this line over here, that's 1/2 of one of the sides. So this length over here is actually S over n. Okay, because half of a side is 1 over n times half of the entire perimeter, because a side is 1 over n times the perimeter. So half of the side is 1 over n times the entire semi-perimeter. What if we're considering either major or minor arc of the entire circle inscribed in the same triangle? Let me answer that later, okay? Because I think it's not going to be relevant to this derivation. I'm sorry I've kind of butchered this derivation. We're going to be done with it soon. So sorry. So this thing here is S over n, not S over 2. Because S doesn't mean a side, S means the semi-perimeter, right? And so what we get over here is that this is S over n, sorry, S over n, and S over n times the tangent of, divided by the tangent of 360 degrees over 2n, and thus the area is equal to RS, which we see here, that's going to be S squared divided by N divided by the tangent of 360 degrees over N. Okay, and here S is equal to semi-perimeter. Okay, so you can write this as a formula if you want. Sorry, it's 2n. 360 degrees over 2n. And if you want to write it in terms of the length of a side, you can do that too. So if you will, if you know, let's say if maybe I'll call L is the side length, then L, so then S, the semi-perimeter is equal to NL over 2. So what do you get? You end up getting that the area is too much, sorry, too much, I don't have enough space to write this. So let me rewrite this on another slide. So just recall area is equal to RS, which we showed on the previous page is S squared over N divided by tangent of 360 degrees over 2N. And now if L is equal to side length, then S is equal to N times L. That's the perimeter divided by 2, right? This is the perimeter. So we instead get NL over 2 squared divided by N divided by tangent of 360 degrees divided by 2N, or this simplifies, this is N squared L squared over 4 divided by N over the tangent of 360 degrees over 2N, or if we want to simplify it, we can cancel out a factor of N, and this turns out to be L squared divided by, or NL squared divided by 4 times the tangent of 360 degrees divided by 2n, or NL squared over 4 times tangent of 180 degrees over n. But again, I wouldn't memorize this formula, right? This is not an easy formula to memorize. It's certainly not a formula that I have memorized, okay? The point of this formula is that you can derive it by knowing that the area of any of these regular polygons is just going to be the radius times the semi-perimeter. Okay, and once you have the radius times the semi-perimeter, if you know a little right triangle trigonometry, you can turn this into a formula involving whatever quantities you want. Okay, so I'm sorry for being a little unclear here with this derivation. I should have practiced it more. But the key is the area is the radius times the semi-perimeter.
Okay.
That's a good form for regular polygons, and then you can manipulate it and get it in terms of other quantities if you want to. James, was there a question?
Yeah, I want you to clarify something to me quickly.
Mhm.
What you have, what you did a cancellation or in, you subtracted the index or
Hmm?
hello?
Oh, over here?
Yeah. One in
Yeah.
that page. Yeah,
Hmm. Yeah, right here.
subtracted index.
So over here, this cancellation?
Yes.
Yeah, so I just did that n squared over n is equal to n. So right, I subtracted the n, right? N squared divided by n to the 1 is just n to the 1. So that's just n.
Oh, okay.
Yeah,
Thank
that's it.
you.
Okay. Yeah. Other questions? Okay, so this is the formula for the area of a regular n-sided polygon. Okay, but you can derive it from triangles, and that's the point. You know, don't memorize this. Memorize things involving triangles. Memorize that the area is RS, where S is the semi-perimeter, And then you can rederive something like this. Okay. We only have a little bit more time, but let me at least do the next two slides. I think I'm not going to be able to do this last slide over here. But okay, so here's a problem involving quadrilaterals. So I'm going to draw a quadrilateral. Oh, wait, sorry. I wanted to say something about quadrilaterals. Let me do the next two slides. So let's just recall that a quadrilateral is a polygon with four sides. And from our work above, we know that the angles in a quadrilateral add up to 360 degrees, right? Because it's 4 minus 2 times 180 degrees. And that's equal to 360 degrees. We know that a quadrilateral can be broken up into two triangles by drawing either of its diagonals. And by drawing both diagonals, we can break up the quadrilateral into four triangles if we want to. And then we have particular types of quadrilaterals. So a parallelogram is a quadrilateral where each pair of opposite sides is parallel. A rhombus is a quadrilateral where all four sides are equal. A rectangle is a quadrilateral where all four angles are equal, which means they have to be 90 degrees each because they add up to 360 degrees. And a square is a quadrilateral that is both a rhombus and a rectangle. What does that mean? Rectangle means all of the angles are the same. Rhombus means all of the sides are the same. So a square means all the angles are the same and all the sides are the same. And then lastly, a trapezoid is a quadrilateral with one pair of parallel sides. Okay? Yes, exactly. The law of division of indices. Okay, so this is just a quick review of what these different kinds of quadrilaterals are. And so now here's a question. I'm going to draw a particular quadrilateral that's going to look like this. Sorry. Okay, so let's imagine that I have a quadrilateral that looks like this, and I'm going to label these sides 13, 12, 4, 3. And so the question is, what is the area of this quadrilateral? The sides measure 4, 3, 13, and 12. Okay, so, we don't have a great formula for so there is actually a formula for the area of a quadrilateral given all the sides, but it's a very opaque formula. It's called Hero's formula, and I don't want to do it that way. Kind of very opaque. It doesn't give you any insight into what's going on. So, what's the theme of today? The theme of today is that everything is triangles, right? So the idea we're trying to figure out an area, what we should do is divide into triangles to figure out the area. That is the idea of today. So we always want to divide into triangles because it's easier to do the area of triangles. So what seems to be the best way to divide this into triangles? Well, we saw from the previous slide, the way we can divide a quadrilateral into triangles is by drawing the diagonals. Okay, and so in this question, diagonal that we're going to want to draw is this one. This is a diagonal of the quadrilateral. And now what do we know? Well, this is a right triangle, right-angled triangle, and the sides are 3 and 4. So if the sides of this triangle are 3 and 4, what does the hypotenuse of the triangle have to equal? Right, since it's a right-angled triangle, right? If you have 3 and 4, the other side has to be 5, right? Because this is 3 squared plus 4 squared equals 5 squared. Right? So, okay. So let me, I assume that's going to be right. But so is the answer going to be 36? Yes, the answer is 36. Good. So James, do you want to explain how you get this? Explanation? Okay, then let me do the explanation, and then because we have to finish at 2:15. So let me do the explanation so we can finish. Well, the idea is now we observe that 5 squared plus 12 squared is actually equal to 13 squared, right? This is 25 plus 144 is equal to 169. Okay, so this is actually true. And what that means is that the other triangle is also right angled. Okay, so there also has to be a right angle here between the 5 and the 12. Right? This is the converse to Pythagoras' theorem, right? Usually we hear the Pythagorean theorem as saying, if you have a right angled triangle, then a squared plus b squared equals c squared. But in fact, the converse is also true in the opposite direction. So if you have a triangle where a squared plus b squared equals c squared, then that triangle is a right angled triangle. Okay, so the converse of Pythagoras' theorem also holds. So this is a right angled triangle. So let me call these two triangles A and B. Well, then the area of A, this is a right angled triangle. The base is 12 and the height is 5. So the area of A is equal to 1/2 times 5 times 12. And the area of B, this is a right angled triangle with base equals 4 and height equals 3. So the area of B is equal to 1/2 times 4 times 3. Well, 1/2 times 5 times 12 is 30. 1/2 times 4 times 3 is equal to 6. So the total area is equal to 30 plus 6, or 36. Okay. So one way that you can figure out the area of this quadrilateral is you draw a good line and it divides the quadrilateral into two triangles. And then you only need to understand things about triangles. And so this is generally a good technique anytime you have a problem about polygons with lots of sides, is to try to reduce it to a question about triangles. Because usually with triangles, it's easier to use formulas to figure out what to get. Okay, so here by drawing the correct line, you divide this quadrilateral into two triangles, and then it's easier to figure out what the area is. Okay, questions? Okay. I'm gonna skip this page because I don't want to I don't have okay. I don't have yeah. All right. I don't have time. So we'll do this next time. So I don't want to rush it. Okay, we'll do this example about rhombuses next time. Okay. So let me just go to the homework because we need to finish up in 7 minutes. So there's two exercises for the homework. Both of them require diagrams, which I'm gonna draw these diagrams on the next page. Okay. So the first one says, what is the area of the segment of the circle of radius 3 shown below where the arc cut off by the segment measures 90 degrees? Okay, so let me just draw the diagrams for the homework exercises. So the first diagram looks like this. Okay, so I'm going to draw a circle like this, and I'm going to draw a segment where the arc is going to measure 90 degrees. All right, so this is going to be 90 degrees here, and I want to know what is the area of this segment right here. Okay, 90 degrees really means, 1/4 of the circle. And what do I know about the circle? The circle has radius 3. Okay, so this is the question for diagram 1. So I want to know what's the segment, and then there's a hint, which is, can you? Yes, my program automatically will draw a perfect circle. If you draw an approximate circle and then you just leave your pen there, then it will turn it into a perfect circle. So in the spring, I'm going to teach you about this program. I don't want to do it right now because it may not be, you need a stylus to do this, and I assume most people don't have that. But yes, my program lets you draw a perfect circle like this. Um, so the hint is, can you add a triangle to the segment in order to make a portion of the circle whose area you know to calculate? So can you turn this segment into something that's a little easier to calculate by throwing in an extra triangle? And then you can find the area of that entire piece and subtract off the area of the triangle, and that's going to get you the area of the segment. Okay, so this is homework question number one. And then homework question number two is, we're given a rectangle ABCD, and I'm giving you a whole bunch of measurements, AM equals MB, AB equals 24, BC equals 18, DE equals X. Then find the value of X such that the area of the region AMED is exactly twice that of region MBCE. So let me draw this picture also. So this is going to be a rectangle ABCD. Okay, so this is going to be a rectangle ABCD. This is going to be the point M over here. So both sides here are 12. AM is 12. MB is 12. BC is 18. So this side is going to have length 18. And I'm going to draw a line from M over here to some point E. This is going to be E. And this length over here is going to be X. Okay, so this is the diagram for the question. And the question is, find the value of X so that this region has exactly twice the area of this region. Okay, and the hint is, don't use the formula for the area of a trapezoid. Okay, you can do it if you want, but it kind of defeats the purpose of what we're doing today. The hint is better. Let's say you forgot the area formula for a trapezoid. So the question is, can you draw appropriate lines to divide the regions into triangles and rectangles? And then basically what you want to do is express this area in terms of X and express this area in terms of X by dividing into rectangles and triangles. Okay? And then if you can do that, then you can calculate this area, and then solve for the value of X that makes one of the areas twice as big as the other area. Okay? All right, so these are the homework exercises for this week. And then last week, thank you for your attention. So next week, we'll begin a unit on solving equations, but we will also do a little bit more geometry. So maybe we will, spend a bit more time on geometry and then begin a unit on solving equations. Okay. So just a reminder here to write your name in the chat if you haven't done that already. I need to make sure that I have your record that you attended. And in particular, if you only wrote your name before I started recording, then please write it now, because once I turn off the recording, I'll lose all of the information for people who wrote their names too early. So I'll keep the recording on for one more minute and then I'll turn it off. Okay, any questions?
Yes, Doc.
Yes, Miata.
How are you today? Thank you.
Good, how
I'm
are you?
I'm trying to ask if you will write you place the assignment question in the chat room.
The assignment, I mean, I send the entire notes to the classroom. So
Oh,
you
okay.
can just find them inside the notes. They're at the last pages of the notes.
All right. Thank you.
I'll send the notes soon.
Yeah. Thank you so
Okay,
much.
you're welcome. And the notes will have the question and they'll also have these pictures so that you can see what it looks like.
Okay.
Yeah.
That's perfect.
All right, you're welcome. All right, other questions? Okay, so in that case, I'm going to turn off the recording.